Hey everyone, welcome to a lecture on Chapter 9, Tides. So what are they? What are tides? They are defined as the raising and lowering of sea level. And if you've lived anywhere on the coast, I'm sure you've noticed this. Or maybe if you've been to the beach successive times and noticed that sea level is kind of varied on either time you've been to the beach, but typically they either occur, you either get a high or low tide once a day, or two high tides and two low tides daily. So tides occur daily, and today we have a really good understanding. Tides are very complex, and predicting tides is a lot of work because there are a lot of factors that affect how sea level will change on different coastlines globally. But we've nailed down a lot of the major factors, and tides can be predicted into the future. They just have little adjustments have to be made for specific circumstances. But tides were recognized by early coastal peoples on Earth. Obviously, if you lived near the coastline, you would notice it. You would notice a tidal range. So high tide would have been when the water is the highest, and low tides when it's the lowest. A lot of times during low tides, you would have to go out and get food. So you would typically take advantage of that once you understand the kind of rhythm of your coastal ocean. But these early peoples certainly understand or notice the patterns between the lunar cycle and our tides. And they noticed that the highest tides occurred whenever there was a new moon or a full moon, and the smallest change in tidal range occurred during quarter moons. So humans must have understood this for a long time, especially to take advantage of the coastal resources that are available to them. But really, Isaac Newton his gravitational law helps explain the relationship of why tides occur. So in terms of the written record, any records of tides don't appear until 450 before the Common Era. So it was until then, and then Isaac Newton came up with his gravitational laws. That was in the 1700s. So yeah, a lot has changed over that time span. So what are the tide generating forces? Well, the tides that we experience on Earth, they're created by the kind of orbital dance that we go through with the moon and the sun. Okay, so the forces that kind of raise and lower sea level are a combination of gravity and the motion of the Earth, Moon, and Sun. The Barycenter, that is when you have two bodies that rotate around a common center of mass. That's referred to as the Barycenter. And the Barycenter between the Moon and the Earth, two objects with a lot of mass to them, it's essentially like the balance point or the common center of mass between those two objects. Now the Earth is much larger than the Moon, so the Barycenter is located close. Here it is on this figure. I'll put a red dot on it. Okay. So if you were thinking of a balance point, okay, say you're balancing a ruler, you would put the fulcrum right at the center of the ruler, and the ruler would be balanced, and that's because there's equal mass on either side of the ruler. Okay, but the problem is the Earth is much bigger than the Moon, and so the Earth has much more mass. And so in order to find the balance point between these two objects that are in motion, the Barycenter, or this fulcrum here, would be pushed all the way towards the more massive object. So this would be Earth. And notice it's not in the center of the Earth. The reason why it's kind of a little outward over here is because of the mass of the Moon. So think of it as as a sledgehammer, right? A sledgehammer is very heavy on this end because it has a metal head on it, and the lighter mass wood makes up the rest. So in order to keep the sledgehammer balanced, the bury point or the fulcrum here would be put closer to the head or the more massive object. Okay. So this image here just really shows us the motion of the Earth. Okay, so the sun is in this direction. The Earth spins in a counterclockwise direction. Okay, and this is the path of the Barycenter as the Earth orbits the sun. This white line is the kind of rotational path of the Earth as it rotates and also orbits the sun, and then this shows you the motion of the path of the center of the moon around our Earth. Here's just a closer look of it. Okay, so the center of mass, or the barycenter of the Earth, is found here. Okay, and it moves in a nearly circular orbit around the sun. Okay, so this here would show you the path of the center of the Earth as it kind of rotates and also orbits around the sun. So in order to understand tides, we have to understand gravitational forces. And so under Newton's law of universal gravitation, every object, regardless if it's kind of a small as an atom or something as big as our sun, if you have mass, you exert a force of attraction towards other objects that have mass. Okay, and so if you have a body with a certain mass, it's going to exert a force of gravity towards other bodies, right? Now what you have to know is if you increase the size of this mass, so if you have 2m, so this is much larger than just m here, that means the force will be doubled. Okay, and if you have an object that has 5 times the mass of this guy over here, then that means the force of gravity will be 5 times stronger. So the take-home message is the more massive the object is, the greater gravitational force it exerts on other bodies that surround it in space. But in addition to that, well, the summary of that is that the gravitational force is proportional to the product of the masses. Okay, so if you have increased mass, you have increased force. Okay, we kind of went over that already. But it's inversely proportional to the square of the separation distance. Okay, so if you were trying to calculate the force of gravity between two objects, M1 and M2, what's really important is how far away or how close those objects are to one another. So the farther an object is away from another mass in space, then the less gravitational attraction there'll be between them. The closer are, the greater the gravitational attraction. So we see that here. Okay, this is understanding gravitational force and distance. Okay, so if you're kind of spacewalking in the kind of orbiting the Earth, so to speak, this is the radius between you, an object with mass, and the Earth. And notice that this radius or this distance is smaller than the one over here. Okay, and so what will happen is that the force of gravity will be diminished the further away you go. Okay, so as the length of the arrows for FG, the gravitational force between the two bodies decreases greatly with increasing distance. So the further away you are, the less gravitational force you'll exert. Okay. So the moon is largely responsible for kind of creating a kind of gravitational forces towards the Earth, and we'll keep it simple. Here the moon is kind of right at the equator, which isn't necessarily true, but just for this example, the moon itself exerts gravitational forces towards the Earth. So wherever you are on the Earth's surface, you're feeling these forces like as if you're being pulled towards the moon. Okay, so the greatest force is on the area of the Earth that's facing the moon, right? Because this spot here on the surface of the Earth is closest to the moon. So that would be the zenith. Okay, the zenith point is closest to the moon. They would have the strongest gravitational attraction towards the moon. If you're on the other side of Earth, this would be the nadir point. This is the furthest distance that you can be to the moon in this example. And so what that means is that exerts the smallest force of gravity towards the moon. Okay, so if you notice, the arrows get longer and longer the closer you are to the moon, and that just indicates the stronger that gravitational force is. So the zenith would be the strongest, and the nadir point, because it's the furthest away from the moon, would be the weakest. Okay, so this is kind of these gravitational forces that are pulling towards our moon. Now there's another force in place. There's the centripetal force, and this is the kind of center-seeking force. It's required to keep planets in their orbits, and is provided by the gravitational attraction between the center of mass, or the Barycenter, of the planets and the sun, and the moon as well. Okay. And what this force is, it tethers the Earth and moon to each other. Okay, and what that essentially means, or another way of thinking about centripetal force, is imagine you have two objects in motion, right? So say you have a ball tied to a rope, and then you're spinning around in a circle. You're in motion, you're spinning, right? And the ball that's attached to the rope is also spinning, and you're kind of wildly swinging it around as you're spinning. If you were to cut that rope, the ball would just kind of fly off in a tangent to the circle that you were kind of spinning around. And so centripetal force is that force that keeps you connected to that ball as you're moving, as you're an object that's moving, and that's the rope. So that rope applies a force to the ball itself and to you, and that's centripetal force. Okay, and if you notice, they're all pointing towards the moon, and all of these lines here are equal length because it doesn't change regardless of where you are on the Earth. Here's that example I was trying to illustrate. Here's a girl swinging a ball in a circle, and so the string supplies the centripetal force, keeping these two objects in motion, connected to each other. So if that string were ever to break, then there's no more centripetal force, and this ball would go careening off, just tangent to that circle, off into space or something. So, but that wouldn't happen because the moon and Earth are kind of locked together in this gravitational dance. So what ends up happening is you have two forces in play, centripetal force and the gravitational attraction. And so the mathematical difference between those two results in a resultant force. And the way to derive the resultant force is to draw a straight line from the centripetal force to the gravitational force. And that's where you get this blue line here. Okay, so if you draw a straight line to here, then what you would get is this blue line. So here, connecting those two dots, then you get that resultant force. This one goes straight up. Over here, it goes straight down, excuse me. And then this, you get that angle. So that's where the resultant force comes on, and that's where the resultant forces that cause tides work on those particular portions of the Earth. And so those are the tide generating forces. So the resultant force has a horizontal component, and this creates bulges on either side of the Earth. And that's what the tides are. They're bulges. Okay. And what I mean by bulges is areas that are kind of raised up. And in an idealized example, and it'll get more complicated as we move along, we're disregarding the continents and thinking of just like a world ocean. And the moon is right at the equator, okay, which is not true. We'll go through that. But the resultant forces essentially create one bulge towards the moon, okay? So think of like the gravitational force of the moon pulling up the ocean, creating those high tides and a tidal bulge towards the moon, and then another tidal bulge away from the moon, okay? And it seems kind of counterintuitive when you think about it. Why would there be two lunar bulges on either side of our Earth? Well, the reason is, again, it seems kind of counterintuitive, but when you consider two objects that are in motion in space, right? The bulge on this side has to do with the water is not necessarily it's like its own mass on Earth, and it's not directly connected to the rock that's in motion in space, and so it kind of bulges out to catch up with the Earth, so to speak. The ocean kind of gets left behind, so to speak. So the second bulge on the far side of the moon, it's the result of an equal but opposite force caused by the motion of the Earth-Moon system. Okay, and so what we do when we experience high and low tides, the Earth is just rotating through these bulges. Okay, let's go to the next slide. There you go. So here are those bulges so you can visualize them. All right, they're pretty big. One is towards the moon and one is on the other side of the Earth away from the moon. Okay, this dotted line here is average sea level. Okay, so if you had a planet with no moon or tide generating forces, that's where sea level would be, or the average sea level. So if you were here, let's say you're a person right here on the Earth, you would be experiencing low tide. And then as the Earth rotates in a counterclockwise direction, you'll be rotating into the bulge of a high tide. And so in 6 hours, okay, approximately 6 and some change, you'll be over here and you'll be experiencing high tide. Yay, right? But then in 6 more hours, the Earth continues to rotate and you'll be on the other side of Earth, like the back side of Earth over here. And you'll be experiencing low tide again. And then 6 more hours will pass and the Earth will rotate again and you'll be over on this side and you would be experiencing high tide. Okay, so those are the idealized tidal bulges. Okay, that's assuming that the moon is at the equator, there are no continents, and it's just one world ocean. Let's go over some terms first. Tidal period, when we refer to that, that's the amount of time between two high tides. And as the example I used last time, that would be every 12 hours. The lunar day, that's the time between two successive overhead moons. So if you were, say you were outside at 8 o'clock at night and you saw an overhead full moon above your head and you're like, wow, that's cool. Okay. How long would it take for the moon or the Earth to kind of rotate around its axis so that the moon is directly overhead in the exact same spot? And that's every 24 hours and 50 minutes. So if you saw a full moon directly overhead at 8 o'clock, the following day it'll be 8:50 when the moon is at the exact same spot that it was the day before. The solar day is measured from the time the sun is on the meridian of an observer to the next time the sun is on that meridian again, and that's 24 hours long. That's our day. The reason why the lunar day is 50 minutes longer than the solar day is because it takes the Earth to move another 12.2 degrees to the east when it's orbiting. So that that's approximately 50 minutes. So the Earth needs to quote catch up to the moon, so that the moon again is on the area directly overhead to where you witnessed it the day before. So that's the reason for the difference between lunar and solar days. So here's a cool example just to understand that. Okay, this is the rotation of the Earth. This is the North Pole, so we're kind of looking at it, from the, I guess, alien spaceship observation, right? Here's a person on Earth, and here it's looking, the moon is directly overhead. Okay, so after the course of 6 hours, they're experiencing high tide. After a course of 6 hours, they're now experiencing low tide. Okay, and then another 6 hours go by, they experience high tide. Okay, another 6 hours, low tide again, and then after the 24-hour period, if you look directly above your head, you wouldn't see the moon in the exact spot you saw it the day before. It'll be 12.2 degrees to the east, okay, over here. So what has to happen is the Earth has to kind of rotate for another 50 minutes, and then to your perspective, the moon will be directly overhead, and that's a lunar day. So every 24 hours, 50 minutes. And so as a result of that, that means that the excuse me, that the on Earth, high tides occur every 12 hours and 25 minutes because it's the tides are dependent on the lunar day, not the solar day. Okay, so if you went to the beach, say like at 1 o'clock in the afternoon, and you were at the peak of high tide, if you went the following day to the beach, the peak of the high tide would be 50 minutes later. Okay, because the moon has the greatest effect on tides, and it's all based on the kind of the lunar bulges. Okay, solar bulges. The sun also exerts gravitational force on Earth, and the sun is much more massive than the moon and the Earth. Okay, here's an image for scale so that you can see just how massive the sun is. Okay, so you would think that the forces that generate tides would be really kind of affected by the sun, mostly because it's so massive. But remember, the sun is really far away. This is also to scale. Okay, so the sun, in comparison to the moon, the distance from the moon and the Earth from the sun is shown to scale here. You can see the sun is very far away. So despite the fact that the moon is so much smaller in terms it's so much smaller than the sun, it has a greater control on gravitational force and tide generating forces on Earth than the sun does, and that's because the moon is so much closer to the Earth than the sun is. But the sun does create bulges as well. We call them solar bulges, but they're about half the size of lunar bulges. Okay, the sun is 27 million times more massive than the moon, but the moon generates a stronger tidal force, and that's because it's much closer. So when you experience tides, they appear to move water kind of towards the shoreline. We call that a flood tide. And it also can move water away from the shoreline, and we call those ebb tides. And that really is just an appearance because the Earth is, the tidal bulges are fixed relative to the sun's and moon's positions and where they are. And essentially, as the Earth rotates and as time goes by, the Earth rotates and moves through each one of those bulges. Okay, let's take a look at the monthly tidal cycle. The next image will show the both solar and lunar bulges. But so the tidal range is the difference between the high tide and the low tide. So let's say it's basically the high tide is the high water mark and the low tide is the low water mark, and it's just measuring that distance. A syzygy is when the moon, earth, and sun are aligned. And that's important because when they're all aligned, that means the tidal bulges are aligned, and that leads to really high tides, or higher than normal high tides. And when the moon is in the first or third quarter phase, that's referred to as a quadrature. And the reason why we kind of define the quadrature is because you have tidal ranges that are smaller than normal during these phases. Okay, and that's because we have competing tidal bulges. Okay, so here's the monthly tidal cycle. Okay, within a month, within one cycle, we have spring tides and neap tides. Okay, spring tides are essentially whenever we have a new or full moon. And when we have a full moon, that means the moon and sun and earth are all aligned, right? And the full moon is being kind of brightened up by the sun. The new moon's not receiving any sun, so it shows up as dark. But both of these scenarios, the moon, earth, and sun are all aligned together. And so what that means is that the tidal range is the greatest. This is a syzygy, okay? The lunar bulges, which are almost twice as large as the solar bulges, are aligned with the solar bulges. And so what that leads to is really high tides and really low tides. So the difference between the low and the high water mark is greatest. Okay. Neap tides, on the other hand, these are the quadratures. This is when we have the first quarter moon, okay, and the third quarter moon. And so the lunar bulges show up on this side of the Earth, here and here, and the solar bulges show up on the other side of Earth. And so what happens is, as you're rotating through all the bulges. And so what you'll find is the tidal range is the least during neap tides, meaning that high tide is not very high and low tide is not very low. So the difference between the high water mark and the low water mark is very small. And so there's not much of a tide. Okay, so those are the spring and neap tides. And the entire monthly tidal cycle occurs at 29 and a half days is the lunar cycle. That's the lunar month, is 29 and a half days. So it's 29 and a half days between two successive full moons. Okay, so here's just some definitions. The new moon, that's when we have a syzygy, and that's when the moon, earth, and sun are aligned, and the moon cannot be seen from Earth. The full moon is when it's, that's direct opposite. And a quarter moon is when the moon appears to be half lit. So this is where you'd get those neap tides. And then the other moon phases, the waxent crescent, that's when the moon is moving towards the first quarter. So it's going from a new moon to a quarter moon. So essentially the area of the moon that's being lit up by the sun is increasing. The waxing gibbous is when the moon is moving from the first quarter to the full moon. To the full moon. So it's the entire surface of the moon, or at least half the surface is being lit up by the sun towards the full moon. And then once you go from full moon towards the last quarter, we call that the waning gibbous. And then the moon moving from the last quarter to the new moon as it's kind of disappearing from view, we call that the waning crescent. I think there we go. It's much easier with the picture. So, okay, there's the 29 and a half day cycle. You go from a new moon, right? So the other side of the moon is being lit up by the sun. They're all aligned. Okay, to the waxing crescent. This is what it looks like after 4 days. Then to the first quarter, right? This would be your neap tide. So we'll do N for neap, right? Small tidal range. Here, this would be a spring tide. And then as we go in this direction, then we'll get to a full moon. So another spring tide, really high tides and really low tides. And then as the lunar cycle continues, Then we'll move on to the third quarter, and this is the waning gibbous, and then the waxing crescent, and then we finish the cycle with the back to the new moon. And this year, after 22 days, this would also be a neap tide. So you just go, in 29.5 days, you go from spring to neap to spring to neap, and it kind of repeats itself over and over again. And that's the different phases of the moon. So just by going outside and observing the moon, you can predict essentially what part of the tidal cycle we're in, even if you're not at the coastline. Okay, everything's been pretty nice and easy, but there are some complicating factors in terms of kind of predicting what the tidal range would be like on any coastline on Earth. One complicating factor is declination. So that's the angular distance of the moon or the sun above or below the Earth's equator. So the sun to the Earth, depending on where we are in our orbit, remember we have a tilt on our orbit to the plane between the Earth and the sun, and that's 23.5 degrees. So the declination of the sun to the Earth, depending on where we are in our orbit, is 23 degrees north or south of the equator. So that means the solar bulges will be 23 degrees north or south of the equator and on opposite sides of the Earth. The moon is 28.5 degrees north or south of the equator. That's its declination. And so what that means is that the lunar and solar bulges, they shift from the equator and they create unequal tides. Let me just show you an image. Okay, so in reality, the moon, yeah, here it is over here. That's a declination of 28.5 degrees from the equator. So the tidal bulges are kind of diagonal like this. So, and then on the opposite side of Earth, here would be the other tidal bulge. And so if you're here and you're in, let's say, I don't know, Saudi Arabia, woo, right? You'd be experiencing high tide, right? Because you just happen to be kind of like on the surface, and the moon is kind of directly in this direction at your latitude. But once you rotate to 6 hours, you'd be in a low tide here. And as you approach over here, if you notice, you're over here and you're experiencing after 12 hours and 25 minutes, another high tide, but this high tide is not as high as this high tide. And so what you're experiencing are two high tides, and one is greater than the other. And the same goes for low tides. One low tide will be lower than the other. Another factor that complicates tides are the elliptical orbits of both the Earth around the sun and the moon around the Earth. So the tidal range is greatest at the perihelion, which occurs in January. This is when the Earth is closest to the sun. And the tidal range is least at the aphelion, which is in July, and this is when we're furthest away from the sun. And the Earth is approximately 148.5 million kilometers from the sun during the northern hemisphere winter, which would be January. Okay, and then during July, the Earth is 152 million kilometers away from the sun. Okay, and that distance means there's a variability of about 2.5% over the course of a year. So sometimes we're closer to the sun and sometimes we're further away. We're closer to the sun in January, which is weird because in the northern hemisphere it's colder, but we're actually 2.5% closer to the sun than we are in July, despite the fact that July is hot. Okay, so in addition to this, the moon revolves around the Earth, okay? And so the tidal range, or the bulges that are created by the moon, is greatest at the perigee when the moon is closest to the Earth. And then the tidal range is, or the lunar bulge is the least when the moon is furthest away from the Earth. And so the moon also has kind of an elliptic orbit around the Earth. Sometimes it's closer, sometimes it's further away. And this cycle occurs over the course of every 27.5 days. And this Earth-Moon distance varies by about 8%. So that's about 233,000 miles. So depend on basically 27.5 days, the Earth could be, the moon could be 8% closer to the Earth or 8% further away. And so what this eventually creates are these cycles between the moon cycles between perigee, apogee, and going back and forth every 27.5 days. Sometimes those cycles line up with the lunar cycles, the 29-day lunar cycles with full moons and new moons, meaning like, what if we have a full moon or a new moon, and then the moon also happens to be closest to the Earth when the sun, moon, and Earth are all aligned. And what that does is that essentially creates Proxygean tides, which are exceptionally high tides, meaning like they have the largest tidal range. So really high tides and really low tides. And that those cycles kind of coincide about every 1.5 years. And this can wreak havoc on low-lying coastal areas, especially if there's a storm to simultaneously occur during a Proxygean tide, when the moon is closest to the Earth and it's also a full or new moon. That can cause flooding, and imagine if there's a hurricane with storm surge. So crazy things can happen when these cycles are all aligned together. Here's just an image of the elliptical orbits of both the moon. Okay, so here's the perigee closest to the Earth. Every 27.5 days, it's a little closer to the Earth than at the apogee, which is further away from the Earth. So lunar bulges will be stronger here and then weaker here. Same with the Earth and its orbit around the sun. In January, as we're rotating around the sun, we're at this position in January. Now, it's greatly exaggerated. The orbits are highly exaggerated just to show the point, but we're closer to the sun in January than we are in July. So if we have like a full moon in January, we'll have really high tides. And if it happens to be the perigee as well for the moon, that would be a Proxygean tide. And here's the size comparison of the moon at apogee and perigee. So the moon appears to be 14% larger. A lot of times we refer to these as supermoons when we have a full moon and it also happens to be at its perigee. So it appears to be much larger than normal, which makes great sightseeing. Okay, and so the idealized tide prediction essentially is that we have 2 high tides and 2 low tides per lunar day. And then there's 6 hours between the high and low tides. But again, that's idealized. Here's what we'd be experiencing. Now we've taken into account the declination to the moon. Okay, the moon's over here. And here's a person experiencing high tide, right? Then 6 hours later, we rotate to the other side of the Earth, right? Then they'd be experiencing low tide. So that would be over here, spot B. Oh, there he is, behind the Earth after 6 hours. So we went from a really high tide to a low tide as we're rotating out of the bulge here and into low tide. In 6 hours again, you'd be back over here and you'd be experiencing high tide again. But if you notice, this high tide isn't as high as the original high tide. Okay, so in the idealized tide situation, assuming there are no continents and it's just a global ocean, this is what would occur. You have a high tide, a really high tide, a low tide, a lower high tide, and then if you rotate again to the next 6 hours, you'll be back to a low tide. And this one will be similarly as low as the first one. And then you're back to the beginning to a really high tide once you go the full lunar day, 24 hours, 50 minutes. So this is kind of predicting what would occur at higher latitudes at essentially 28 degrees, which would mean that you're at the ideal spot, to have the declination towards the moon. If you're at the equator, you would experience more similar high and low tides. You see, you have still 2 high tides per day, and they're both high tides and low tides are very similar to each other. And then if you're at the 28 degrees south latitude, you have the same high tides, but they're delayed by 12 hours in this situation. But those are idealized situations. When we look at what's actually happening on Earth, we have real tides. And real tides, the ocean water and the continents that exist on the surface of the Earth kind of stop these waveforms from kind of moving through the entire ocean. The continents and friction with the seafloor modify these tidal bulges. Okay, so tides are shallow water waves, and the idealized tidal bulges cannot form on the Earth with continents because they cannot keep up with the rotation of the Earth. So what ends up happening is you get these crests and troughs, and the tides rotate around these central points, and we call those amphidromic points. Okay, so these tides kind of roll around these points, and specifically at the amphidromic points, there's no tidal range there. And radiating away from these amphidromic points are co-tidal lines. And what that means is along those lines, those areas of the ocean experience the simultaneous high tide. And that tidal wave rotates around these amphidromic points every 12 hours. Let's take a look, an image of these. So those amphidromic points are here. Okay, here's one. Here's another. Okay, so they rotate in a counterclockwise direction from 0 to 10. Okay, and so the co-tidal lines, for example, this blue line here, everywhere on this blue co-tidal line will be experiencing a high tide at the exact same time, and then in 2 hours, this line over here, 4, will be experiencing the high tide. And then it rotates around these amphidromic points until it returns back to this co-tidal line here. And there's a number of amphidromic points in different parts of the ocean. And so this is the delay time of lunar high tide hours between each amphidromic point. And so large swaths of the ocean will experience similar high tide times as a result of these amphidromic points. And here's a cotidal map of the entire Earth. And so as a result of this, we get some unique tidal patterns because every ocean basin's different, every continental margin's different, every coastline's different. They're at different latitudes, all different types of conditions. And so each area of the Earth has its own kind of tidal pattern. Diurnal tidal patterns are where you have one high tide and one low tide per day. Okay, so almost like every 12 hours, 25 minutes, you have that shift. Semi-diurnal and mixed tides are every 6 hours, and you'll have 2 high tides per day and 2 low tides per day. And the tidal range is about the same. So you have 2 high tides that are at the same height and 2 low tides that are at the same height as well, or low, so to speak. So the tidal range is not different between the 2 high tides and 2 low tides. The mixed tidal pattern is when you have 2 high tides per day, but the tidal range is different, meaning that you have a high tide that's really high, and then you also have a high tide that's not so high, a low high tide. And then you have a low tide that's very low, and then the second low tide is not as low. Okay, so let me show you what this looks like graphically. Okay, this here would be the diurnal tidal pattern. So in a tidal day, from here to here, you have 1 high tide and 1 low tide. This distance from here to here would be the tidal range. And so anywhere where you have this kind of orange on the coastline, that's where you'll have that tidal pattern. and that's true along the west coast of Florida and a lot of the Gulf Coast states and into the Yucatan. They have the diurnal tidal pattern, which is very easy. It's very nice. It's one kind of high tide, one low tide. Easy, right? The semi-diurnal tidal pattern is, so here is within the tidal day, okay? You have two high tides, one here, and two low tides, one here and one here. And the two high tides are at the same height, and the two low tides are at similar heights as well. And that's east coast of Florida, all east coast of the United States, west coast of South America, mostly the west coast, some parts of Central America, Africa, Europe. A lot of places have the semi-diurnal tidal pattern. And then finally, the last tidal pattern where we have on the west coast of the United States. So if you go to California, for example, you'll have within a tidal day, you'll have a high tide, right, followed by a really low tide. Okay, so big tidal range between those two, huge tidal range. And then the subsequent high tide is not as high. Okay, see how it's lower than the previous high tide? And then the next low tide is not as low as the previous high tide. I mean, sorry, low tide. God, I'm getting you guys confused. But here, the point is, this tidal range is much smaller than this tidal range. And that's a very common tidal pattern on the west coast of the United States. Here are the monthly tidal curves, okay? So you have those kind of daily high and low tides, but then here you can see in an entire month, you've got the neap, spring, neap, and spring cycles in as well. Remember, neap tides, your tidal ranges are smaller because of the the moon and sun are at right angles to each other, which minimizes the tidal range. So here are those daily tidal ranges, and if you notice, they're not sweeping back and forth really high. But as we approach a syzygy or a spring tide, the tidal ranges increase drastically. Okay, so you can see in an entire month, for example, here in Boston, Massachusetts, you go from neap tides to spring tides to neap tides to spring tides. And you have an increase in tidal range here, back to a decrease, and that's the kind of rhythm of the tidal patterns, monthly tidal patterns in Boston, Massachusetts. Look at San Francisco. Remember, San Francisco has the mixed tidal pattern, so it's a little crazier. It almost looks like a heartbeat, where you have big high tide, big low tide, then not so big, and back and forth. And they're really exaggerated during spring tides, and then they kind of taper down during neap tides, and then they get big again in the spring and go back to neap, back and forth. Okay, and then this is the last example here is in China. They have a diurnal tidal pattern. This would be similar to what we have in Panhandle, Florida, where you have one high tide, one low tide per day, and it's large. Tidal range is big for spring tides, and minimal for neap tides. So it kind of expands and contracts, expands and contracts. Okay, so it's pretty cool to look at these patterns. And so when you have tides in coastal waters, you can have situations where the kind of geometry of the coastline and also the topography of the ocean floor kind of amplifies the tidal range. Okay, so tides can be reflected by the coast and amplified. And this is really apparent in the Bay of Fundy in Nova Scotia. This has the world's largest tidal range. The Bay of Fundy has a really wide opening into the Atlantic Ocean, but as you go northward, its northern end, it splits into narrow basins. Okay, and in the Manassas Basin, the tidal range is 56 feet, or can be during the spring tidal range is 56 feet. That's 5 basketball hoops, one on top of another. Okay, there's some really cool, I guess, time-lapse photography in the Bay of Fundy showing you what high tide looks like, and then over the course of time show you what low tide looks like, and it's pretty dramatic. You can kind of see it here. You got to time your fishing trips so that you can leave the harbor during high tide, because at low tide you're stranded. you're not going anywhere. And so here's the entrance to the Bay of Fundy. It's very wide. And then here are those two narrow channels. This is the Manassas Basin. This is where you have the highest tidal range. In addition to that, the Coriolis effect also, has that curving to the right. So when you have tidal currents that move in, they move in even stronger because of the Coriolis effect as well. Then there are tidal bores. These are walls of water that can move up certain rivers. This really is in specific areas where it can be dramatic. In some cases, surfers can take advantage of these tidal bores coming into certain rivers and actually surf the incoming tidal currents, which is pretty crazy. And so it's essentially, it's like an abrupt flood tide comes in, and you have a short ebb tide phase, and the low-lying river with that seaward current creates these tidal bores that move in. Okay, let's see if I have a picture. Okay, no, I don't. All right, but those are tidal bores. Then there are rotary currents. This is a current that slowly turns as the tide crests in a basin in the northern hemisphere. They rotate counterclockwise. They can affect kind of enclosed bays. So essentially, it's like a rotating high tide through a basin, and then the rotary current changes to an alternating current, or what we refer to as a reversing current, and then that moves out of really narrow coastal passages and can be quite dangerous. Navigating ships in these enclosed basins can be pulled out drastically with these tidal currents, and some catastrophically. Some of these boats can sink with tidal currents that are really strong like that. The coastal tidal currents, when you have water rushing up a bay or a river with an incoming high tide, we call that a flood current. An ebb current is when the water drains from a bay out into the ocean. And then there are two times in between the movement of ebb and flood currents. We call them slack water, either high or slack water times or low slack water. This is when there's no flood or ebb current, and you have essentially minutes of being around with no tidal current. So high slack water occurs during the high tide, and low slack water occurs during the low tide. So this shows you the coastal tidal currents that can occur in certain areas. So when you're at the this is the low tide. Okay, so as you're approaching low tide, you'll have an ebb current pulling water away from an enclosed area out into the open ocean. So here's a time of high velocity in terms of, this is the current velocity. So you have high current velocity during this time. Okay, but once you hit low tide, this is the low tide slack water, the velocity dies down. Okay, so this is where the low tide slack water would be. There's no water velocity or any current, okay, because the ebb current velocity has kind of risen and fallen to the low slack water. Okay, but once you're at the absolute low tide, then as you approach high tide, the flood current comes in, right? Comes into the coastal area. So you see the velocities of the flood current reach kind of a maximum, and then they slow down as you approach the high water slack water mark, which is right here. So after 12 hours and 25 minutes, you're officially at the high tide. And there's the velocity of the flood current is non-existent. In fact, there's no moving current at all. But then as you approach the next low tide over here, then you have a very strong ebb current, and all that water is coming out of an enclosed area, very fast velocities, until you approach the low slack water or very low water, low tide here. And then it repeats itself. Here's the next flood current. You have increased flood or current velocities as you approach the next high tide. Other crazy situations can occur with incoming coastal tidal currents. You can have whirlpools. These actually exist. These are rapidly spinning seawater in restricted channels. Typically, if you just happen to have two connecting basins with different tidal cycles, then you can have two currents kind of moving in opposite directions begin to create a whirlpool. The most famous example is the maelstrom in Norway. It's the Arctic, off the coast of kind of like the really northern latitudes of Norway. I think we have a picture in the next slide. Yeah, here we go. Here's a boat getting caught up in one of those whirlpools. They occur over here. So it's really in specific situations you can have this. There's some in the Mediterranean Sea. Off the coast of Italy, I think there's one. And sailors would always kind of talk about the kind of crazy, swirling, currents in the ocean. And they can pull boats towards them, but most of them aren't significantly strong. They kind of just you get pulled into them, and then you have to kind of navigate your way out. But it's something that does occur. Okay, so really unique situation. Another really crazy and unique organism that kind of times the tides really well and almost perplexing are the grugnon fish. The grugnon fish is like a small silvery fish. It's about 6 inches in length, and it comes out of the water in California to spawn. The females go in and lay their eggs, and the males fertilize them, and they kind of bury it into the sand on the beach. And so these fish only spawn after each night's higher high tide has peaked, and then on the 3 or 4 nights following the highest spring high tide. Okay, I know that's hard to make sense here, but let me just work through it. Remember, on California, they have the mixed tidal pattern. So there's a high tide and a lower high tide. So somehow these fish realize it. It might have to do something with their like pressure sensing with water depth. But during a new or a full moon, they'll come in during the higher of the high tides during that day and spawn, and they'll lay their eggs. Okay, and the reason why they do this is that after the new moon spring tide, the sediment on the beach will be depositing as you have successive days of diminishing high tides, and for the next 3 high tides after the spring high tide, the fish come back to lay more eggs, and more sediment that's building up on the beach. Here's an image of them spawning, and they're half in the sand, and they bury their eggs, fertilized eggs, in the sand, right? And so they do this 3 days in a row after the new moon or the spring high tide. And the reason is because sand is being deposited on the beach with successive lower high tides. Okay, then after the course of 6-7 days, the tidal pattern here, if you notice, the high tides kind of hit a low, and then the high tides start increasing in height. And as the high tides increase in height, each successive high tide erodes sand from the beach, so it starts exposing the fertilized eggs. Boom, and these fish hatch. And that happens on every successive high tide until the full moon spring tide, and then the fish start spawning once again and laying their eggs in the sediment. That's insane. How do they know? Right? So and what scientists have, they've actually had these eggs in a lab, and the eggs will only hatch if they're subjected to some environmental stressors, like as if sand was being removed from the beach to mimic the incoming rising tides every day, or the higher high tides, and then the eggs would hatch. If that doesn't happen, the eggs won't hatch. So these organisms are specifically tailored to this mixed mode tidal cycle, and their life or their life cycle is like intertwined with the rhythm of the tides there, which is pretty crazy. Okay, so to kind of wrap this up, tides can be can generate power as well. Tidal water can be trapped behind coastal barriers, and then that water can be kind of channelized into certain areas to spin turbines and to generate power. Okay, so tidal currents and narrow channels can be used to take advantage of this, which is a great source of renewable energy. But the problem really is it doesn't produce power on demand. We like our electricity in our homes now when we need it, not when tidal currents are their fastest, right? What about during those high slack water times? There'll be no power generated during those times. But a lot of these tide generating power plants, they have some harmful environmental effects because they can mess with migration of organisms in and out of bays or in and out of those channels. But it is a renewable resource, which is a good thing. The first Asian power plant was built in 2006, and the United Kingdom has also proposed building the largest tidal power plant. But here's an example of the Laurence one in France. Okay, so they have a bridge across a narrow channel. Okay, and what happens is you create kind of like a barrier, and then you have a lot of water on one end of this, allowing water to flow through a turbine and filling the falling side. So during an incoming high tide and outgoing low tide with the ebbs and the flood currents, you can take advantage of that to create energy, which can be very useful. Okay, thank you.